Hello everyone, my name is Tony Burke. I am an instructor and blogger, and today I'm going to talk about one of my favorite data center technologies, which is storage. Now, recently I've seen some talk about fiber channel over Ethernet with regard to fiber channel and storage in general. There's been a lot of misconceptions about fiber channel over Ethernet, and I'd like to clear some of those up. Let's go over some fiber channel basics and some fiber channel over Ethernet basics, and hopefully that'll clear some of that technology mystery up. So let's take a look at fiber channel. So fiber channel is a lossless protocol because fiber channel runs one type of traffic primarily, and that is SCSI. Now, when SCSI was first created, it meant to go from the motherboard via a ribbon cable to a hard drive. And that distance was about 1 meter or so, depending on the cabling. Maybe there's some external cabling that took up some more space, or took up some more distance. But for the most part, SCSI wasn't built to go very far. As a result, SCSI didn't have a whole lot of error correction or what to do when things go wrong. So SCSI messages don't like to be dropped. When they created fiber channel, they realized this limitation, so they created a lossless protocol. Now take that into contrast it with the TCP/IP stack. The TCP/IP stack was literally meant to go around the world, so a lot can go wrong because you have an unknown number of network devices, routers, and switches, and unreliable connections, undersea cables, etc. So it was built to be very resilient. TCP can retransmit segments, UDP, datagrams. We just don't care because of the overlying protocol. But in fiber channel SAN, we are a lossless protocol. So that means that we guarantee delivery 100% of every frame going from one side of the data center to the other. The only real way to drop a frame in fiber channel is if you cut a cable, power off a switch, or you have an extreme case of credit starvation because there's something really going on. Fiber channel frames typically have a time to live inside of a buffer of half a second, but that's an eternity in the switch world. So in normal day-to-day operations, we guarantee losslessness in fiber channel. So let's talk about how we do that. The way that we do it most of the time is with something called Class 3 services in fiber channel, and that provides a port-to-port or basically port-to-port flow control. So here's how this flow control works. I've got two switches here. I've got switch 1 right there. I'm going to switch colors here. So I've got switch 1 right here, and I've got switch 2. And I've got a fiber channel link in between them. Now this could be any speed link, 1, 2, 4, 8 gig, 16 gig, doesn't matter. Every port has an ingress buffer and an outgoing buffer. So buffers are where we store frames before they can get serialized out. What will often happen is that this outgoing buffer will have a couple frames in it. Only one frame can be serialized out of an interface at a time, so if you have more than one frame waiting, you have to put it someplace, and that's where you put it into a buffer. So we've got these frames ready to come out of that interface and go to the input buffer of switch number 2. Now, what can happen is this input buffer, for whatever reason, is full. So what would happen if we sent a frame to this full buffer? Well, it would get dropped. But we don't do that in fiber channel because we have a mechanism called buffer-to-buffer credits. So buffer-to-buffer credits. When these ports come online, they negotiate how many buffer-to-buffer credits they have. And a credit is a space for a single fiber channel frame. So a common value is 16, so we have 16 credits. So they initialize, they know that each other has 16. I've got 16 spaces in this input buffer, and I've got 16 spaces in this input buffer ready and reserved for these fiber channel frames. So when switch 1 sends a frame, it knows it can send up to 16 frames without getting an acknowledgement. But every time it sends a frame, it has to decrement its credit by 1. So I sent 1 frame, I get 15. I set 2 frames, then I send 4 more. And eventually, if I send 16 frames without, and I don't get any acknowledgement back, I can't send any more frames. So I'm always keeping track. So the sending port is always keeping track of how many buffer credits are available on the receiving port. Now, the receiving port, switch 2 in this case, is going to be able to process these frames. They're going to send them to other ports on that same switch. So once it processes those frames, it frees up credits, and it sends a message, it signals back to the sending port, hey, you have 2 more credits available, or now you've got another credit available. And that way we guarantee that on a port-to-port basis, we're not going to overwhelm your input buffer. So we can do losslessness on a port-by-port basis in Fibre Channel. So this is port-to-port losslessness through these buffer-to-buffer credits. So here I'm using red as a Fibre Channel interface. So we've got a host here, and we've got a storage array here. So from port to port, I'm guaranteeing losslessness. Now that would guarantee losslessness on an end-to-end basis. There is a way in Fibre Channel called Class 1 or Class 2 that will do end-to-end messaging, but we don't really use it. We typically use just Class 3, which says only port-to-port, but the net effect is that we get end-to-end losslessness. Which is what we want on Fibre Channel because, again, Fibre Channel primarily carries SCSI traffic, and SCSI traffic doesn't like to get dropped. The question, what happens inside of this switch? Is there ability to drop frames inside of a switch? Well, potentially, yes, but Fibre Channel takes care of that. And this really depends on the switch itself, the mechanism, because we have to do what's called a lossless internal fabric or a lossless internal switching. And there's a couple ways to do it, I believe. I'm not familiar with how Brocade does it, but Cisco with their MDS line does it with the virtual output queues. So basically, we have frames entering port 1 and frames entering port 2, and they're all destined for port 3 to go out port 3. So a frame enters the input buffer of port 1 and the input buffer of port 2, and they need to get switched across the backplane to port 3's output buffer. So they are destined for there. What can happen in a congestion scenario is that let's say these ports are 8 gig. And this is also an 8 gigabit port, or it could be a 2 gig port or whatever. We can get into a scenario where this output buffer actually gets full. Let's say these 8 gig ports are trying to both push line rate out port 3. So that buffer is full. What will happen is that these input buffers on ports 1 and 2 will not send a frame to the output buffer of port 3 unless there's space. There's some sort of signaling mechanism and arbitration going on inside of the switch. And again, Fibre Channel doesn't care what that mechanism is. It just cares that there is a mechanism to prevent that buffer overrun. So if that buffer is full, then the input buffers on port 1 and 2 do not send the traffic, do not send their frames over. So what happens when they get full? Well, they starve out the buffer-to-buffer credits on the sending ports that are connected to ports 1 and 2. And this is congestion. Now, something to keep in mind, Fibre Channel cannot fix congestion. Congestion can happen. Buffer-to-buffer credits do not solve congestion issues. If we're trying to push 2 interfaces at line rate out of another interface that's the same speed, we're going to have congestion. That's just the way networking works. Buffer-to-buffer credits cannot fix congestion. What they do is prevent packet drop or frame drop in Fibre Channel parlance, which is what we want. But we can still get congestion. We can still get a slowdown. So congestion is fixed primarily by adding more bandwidth, adding more links. So as port number 3 serializes some of these frames, then we can start to empty out the input buffers on ports 1 and 2 and fill them up again. The virtual and virtual output queues fixes another problem called head of line blocking. So let's say I've got port 4 here, and port 4 is going to have its input and output buffers. So let's say port 2 has a ton of frames that are trying to go out port 3. And port 3's output buffer is full. Port 4's output buffer is completely empty. Now I'm going to use a different color to represent a frame destined for port 4. There we go. It's back of the line, but however, because port 3 is full currently, the output frame that's destined for port 4 gets to jump the line and will go into its output buffer. So that's what the virtual and virtual output queues mean. Basically, virtual output queues mean we're keeping track of the space available in all of the external ports, and that way we can we can jump the line if we need to if a port is congested. So again, Fibre Channel cannot fix congestion. Fibre Channel handles congestion in a very particular way, which is through buffer-to-buffer credits. And congestion is basically any time we have 2 frames or more than 1 frame, trying to leave or enter an interface at a given time, because we can only send 1 frame at a time. So Ethernet works in very much the same way. In Ethernet, we actually do have a choice, though. Well, first of all, let's talk about the input and output buffers in Ethernet. So Ethernet has input and output buffers. When we send frames from, so we have an output buffer, we send frames over the wire and they end up in the input buffer of the receiving port on a switch. So I'm assuming these 2 connections are actually switch to switch. Now in Ethernet, when we have congestion, the first thing we do is we buffer. So if we have more than 1 frame in this input buffer or more than 1 frame in that output buffer, that means we're waiting to serialize or waiting to forward on frames. So that indicates a little bit of congestion, which is fairly normal in Ethernet. That's the way switches work. But we have a choice. Once we fill up those buffers, something else has to give. Normally, by default, Ethernet switches and Ethernet devices in general are set to drop. When our buffers get full, that's what we do, we drop. We either drop them, tail drop them, or we can do some proactive dropping, something like weighted random early detection, or WRED. The other choice that we do have as an option, and we've had this option for a long time, is we can pause them. And this is Ethernet flow control. Ethernet flow control has been around for a while. There's 802.3x, which is old-timey or old-fashioned Ethernet flow control. And I call it old-timey because it's actually been around for a while, I think since 1997. There's also a newer style called 802.1 QBB, also known as priority flow control. 802.3x, the original flow control, stops all traffic on an Ethernet interface. 802.3 QBB will stop traffic based on a class of service marking. So class of service is a 0 to 7 value that is in the 802.1 Q header in Ethernet. So that's VLAN tagging. So VLAN tagging includes the VLAN ID, but it also includes that class of service value between 0 and 7. So we can pause some of the class of services and let other services get overrun and fill up buffers. So when we fill up a buffer, we have 2 choices. So this input buffer on this port here is full. What do? By default, the next frame that hits that interface will get dropped at the receiving port. But we can also set up pause. So what that does is we're going to have to set up a threshold, because we do have a timing issue here. Let's say 80%. If this buffer is 80% full, then we're going to send a pause. And that'll tell the sending port to stop sending frames. Now this pause will have a timeout value on it, on a certain number of milliseconds. And also we can also send a pause 0, which means start sending again. So we can either proactively or reactively send, or tell the signal of the sending port that it can send frames again. And while it's paused, this output buffer can start to fill up as well. So that allows us to do flow control internally on, or flow control externally on an Ethernet switch, so we can make sure that we do not drop a frame between two physical ports. What we can get into, and what will happen on most switching platforms, regardless of the vendor, is that we can do internal lossfulness. So this is not virtual output queues yet. Internal losslessness is that when we get frames that on the input buffers of these interfaces are sending to the output buffer of port number 3, this is an Ethernet switch, that output buffer can actually get full. So what do we do when that output buffer gets full? Most switches will drop the frames. Most switches, port number 1 and port number 2, do not keep track of the output buffers in port number 3, so we don't have that visibility in it. Some switch platforms, however, like the Nexus, the Cisco Nexus 7000, 6000, 5000 series, do have what's called the virtual output queues, and it works just the same way as it works in Fibre channel. In fact, that's where we got this concept from on the Nexus switches, is from the Fibre channel switches. We have a fabric arbitration, so that's the internal switch fabric, so that we keep an eye on the input buffers, keeps an eye on the output buffers of other ports, so that if we run into a situation where this output buffer is full, so we've got a lot of frames coming in on port 1, we've got a lot of frames coming in on port 2, and they're all destined to go out port number 3. Port 1 and 2, their input buffers, keep an eye on the output buffer of port number of input buffers on 1 and 2, keep an eye on the output buffers of port number 3. And if the output buffers are full, then they will continue to buffer. Now what happens when these input buffers fill? We have that threshold, remember? They will send pause frames to tell the sending ports to hold up. And this is congestion. Now, again, congestion cannot be fixed by either dropping or buffering. We have a consequence either way. So congestion cannot be fixed by buffering or by dropping. Congestion is congestion. The only way to fix congestion is to add more bandwidth. So in that way, in Ethernet, depending on the Ethernet switch, we can do end-to-end flow control, and we can guarantee end-to-end losslessness on Ethernet and on Fibre channel. That's where FCoE that's how FCoE works. FCoE requires a lossless Ethernet fabric. And I've just showed you how that can be done on certain switching platforms that do these virtual output queues. So in the Cisco world, we can do Fibre channel over Ethernet on certain switching platforms, such as the Nexus 7000, 5000, 6000, and a few others. Because they have this lossless backplane. Take a Catalyst 6000 or Catalyst 6500, for example. They don't have this lossless backplane. They don't have this fabric arbitration, at least the way that the Nexuses do. So they can't ever do Fibre channel over Ethernet. So what we end up with is the ability to have a fully lossless fabric that we can send, because Fibre channel over Ethernet, all we're doing is we're taking a Fibre channel frame and we're encapsulating it into an Ethernet frame, then sending it and forwarding along over our Ethernet network. So both Fibre channel and Fibre channel over Ethernet provide a lossless platform to send our SCSI messages back and forth. And really, in a Fibre channel over Ethernet network, we don't really care whether the interface is Fibre channel or Fibre channel over Ethernet. For example, this is a fairly common scenario, especially with UCS. So this device right here might be a Fabric interconnect. The host is connected to the top of rack switch, or in our case, a Fabric interconnect, and they're communicating over FCoE. So the blue there is a 10 gig FCoE interface. The rest of the fabric in this diagram, denoted by the red squares, is Fibre channel. We still do Fibre channel services. We have domain IDs on the Fibre channel switches. We do zones. We distribute zone sets. This implementation is sometimes referred to as Edge FCoE, or at least that's what I call it. But Fibre channel over Ethernet can be mixed with a native Fibre channel network. Again, we don't really care what the port type is because we're still doing the same fabric services. So let's say we can actually make this next switch right here FCoE. So now that is an FCoE switch. So those interfaces are Ethernet. So these are Ethernet FCoE interfaces, and these interfaces are Fibre channel. And it doesn't matter because we're still doing N ports and E ports. So these actually are 2 E ports. These are 2 E ports. This is an F port. This is an N port. This is an N port. This is an F port. Now the only difference is because they're Fibre channel, these are Fibre channel over Ethernet, these are VE ports. These are just regular E ports. This is a VN port, and this is a VF port. That's the only difference. But they're still treated the same way. VE port is treated like an E port, so that is considered an ISL, an inter-switch link. So that's how Fibre channel over Ethernet and Fibre channel both provide a lossless network to send your SCSI frames. Neither of them will drop frames under normal operating conditions. There are extreme cases where you'll drop a frame. Say you trip over a cable, that's going to drop a frame. But they both provide a lossless network for your SCSI and storage traffic. So hope that cleared some stuff up. Again, my name is Tony Burke. If you have any questions, I'd love to hear from you. I'm at tburke, that's TBOURKE, on Twitter. And you can also find me on my blog at datacenteroverlords.com. So thank you for watching, and I hope you found it useful.